Well, we are moving on, and just now we are going to learn a lot of interesting things about neural rendering technology. Timur Kutsenko will tell us what is this. Timur, do you hear us?
Yeah.
How are you doing today?
Great, thank you.
Hello, Timur.
Are you ready?
Hi. Of course.
Timur, we are giving the floor to you. Welcome.
Thank you. Hello everyone. I'm Timur Kutsenko, representing a data science department. Today I'm going to show you a new exciting technology for rendering using deep learning. Let me introduce myself first. My position is data scientist and machine learning engineer. I have worked in this area for 1 year. My domain expertise is computer vision and natural language processing. Also took part in some Kaggle competitions. So here is plan for the report. At first, we are going to look at classical rendering and see what neural rendering is. Then dive into the NeRF technology and the main concepts. Next, see some exciting renders and compare it with existing technologies. And finally, discuss some application opportunities. Let's begin. So, what classical rendering itself? Rendering or image synthesis is a process of generating 2D flat image from some 3D scene. Every scene contains 3D model or shape, texture, and light sources. Classical rendering algorithms work from physics perspective, trying to apply texture to a 3D model, calculate all the proper reflections, considering how light interacts with specific material, and project the render onto a certain viewpoint. And the resulting image is called render. These scenes are usually created and designed using some professional 3D graphical software like 3ds Max or Blender. But what if I tell you that everyone with a common phone camera without any LiDAR module can create almost identical 3D scenes just in a few minutes? The only requirement is the scene has to exist in reality. And you can reach it, of course. So how does it work? We are going to reconstruct a 3D scene from a handful 2D images taken from different angles, as we see on video. After scanning was completed and processed, we can get shape, texture, and even lighting and reflection effects. And after some manipulations, scene can be exported as a mesh to any graphical software. So, while classical rendering, given the scene specifications, can render photorealistic image, approximating how physics behave in the real world, a typical neural rendering approach takes a set of input images corresponding to an existing certain real-world scene and builds a neural representation from them. This neural representation is like the source from where we render our final image. Basically, rendering brings the promise of addressing both reconstruction and rendering. Now, let's dive into the concept of neural rendering, or using such things as neural radiance fields, or NeRF in short. As you may already guess, we are going to use common neural networks to perform image rendering. NeRF generates novel views of a scene by optimizing a volumetric function using a sparse set of input views. In the current scene, we have a track and just 2 images taken from different positions. But real collection data to feed the NeRF is look like a bin-red carpet photographer trying to capture a celebrity's outfit from like every possible angle. NeRF takes a set of input images of a scene and reconstructs the complete scene by like interpolating between images. And the actual NeRF prediction or render would be a novel image, like let's say somewhere between. One interesting thing is that NeRF uses deep learning in a little bit of a different way. If you ask someone, how would you come up with this problem using common deep learning approach? they would probably tell you I need a training dataset X as some number of input images, and the target would be the scene itself. And finally, we will be able to get predictions from new set of images.
Excuse me, sorry for interruption. Yeah, Timur, unfortunately, we have some technical problem with your presentation, so could you please share it and scroll down a little bit so we saw only your first slide. So there is some technical issue, and I hope we will fix it right away.
Oh, sorry. Do you see it now?
Yeah, could you please just scroll to the next slide? Yeah, now it works. Yeah, thank you very much. Sorry for interruption.
Okay, let me then retell a bit. One interesting thing is that NeRF uses deep learning in a little bit of a different way. If you ask someone how would you come up with this problem using usual deep learning approach, they would probably tell you I need a training data set X as some number of images, and the target would be the scene itself. And finally, we would be able to make predictions using a new set of input images. But in the case of NeRF, it's not so. Our goal here is completely overfit a particular neural network to one particular scene using only the images of this scene. And if you want to capture a new scene, we need to train a new different neural network. And the result of the training will be our scene represented in the weights of neural network. And this is called implicit representation of scene. Scenes for classical rendering represented a set of polygons, textures, light conditions, and many other. This is called explicit representation. Generally, difference between implicit and explicit is using implicit one, you can't edit scene afterwards, saying you can't edit weights inside our neural network black box and expect that some new object would appear in a scene. For example, like a tank that is being pulled by a tractor. Representing scene as a weights is actually much more compact way of storing the scene. The complete scene may weigh just a few megabytes. So let's bring out what is an actual input and output for training a NeRF model. It can be a bit complicated, so be really attentive now. Here we have our tractor as a real-world 3D scene and appropriate images with the unknown positions of camera inside the scene. Camera position of an image is defined by 3D location and the viewing direction. These camera positions aren't collected somehow specially. There is such algorithms as structure from motion, what can calculate all these values from raw images of the same scene. So this is how NeRF works. For every pixel in the image, we shoot a so-called ray through our scene and equally choose points along this ray. Every point has its own 3D position and 2D viewing direction, like from what camera we see this point in the space. This 5D vector is exactly our model input. Model here is just simple feed-forward neural network with 9 fully connected layers and 256 neurons at each layer. So we query our neural network for every point, and the output would be RGB color and the density. For example, for this point, we would have something like color is yellow and 100% density. And for this point, whatever is color and 0 density. Like we don't care about the color if there is nothing in the space. So this is a really different way we train our neural networks for computer vision tasks. There is no images as input and whatever is output. There is only a position and the viewing direction. If we plot these densities Gauss rate along the ray, we would get something like this. On the x-axis, there is a position of a point along the ray, and on the y-axis, there is a density in the point. The first curve shows us that at the beginning of ray 1, there is nothing. But when the ray hits the bucket, the density goes up. and when the ray comes out, the density respectively goes down. The main idea behind this fancy density curve, what I have just shown, is that we can use such technique as volume rendering. Bear with me, it's the last concept to understand. Volume rendering accumulates colors and the densities along the ray to get a final pixel, what we should see from the camera position from where we shoot at that ray. This allows us to represent such transparent things as windows and see-through it. For example, we have some colored red window, it's transparent, or in another way, it has low density, and we can say some stuff through it. Volume rendering allows us to see stuff through it and make it colored in a bit of a red, because the window color is red. Or another example, if we have fully opaque wall and we can't see any stuff through it because the wall is completely dense and like can't pass any light through it. Here is the formal definition of volume rendering. The viewed color is equal to the weighted combination of colors and the alpha values at each point along the ray. This alpha means how much light we can pass through a point individually and equal to the 1 minus e to the combination of density and the distance to the next point. And the weights are accumulated product of all alpha before and means how much light we blocked earlier before reaching this point. And finally, the coolest part about volume rendering that the whole process is differentiable, the same as differentiable our neural network that produces these densities and colors along the ray. So we can differentiate it and update weights of our neural network. Let's quickly review the whole process NeRF does for training. At first, we take some images of a scene, apply structure from motion algorithm to get camera positions and viewing directions, calculate rays for every pixel of every image and sample points along them. Pass these points to neural network to get densities and colors. And apply volume rendering for every ray to accumulate color and finally calculate the difference between predicted color and what we can observe in the image. That is basically it. Converging to good results with this structure scene takes about a day. Yeah, sounds like eternity, but we'll talk about this a bit later. To get the predictions or actual rendering, we just query our model at a specific location and the viewing direction multiple times and get our predicted image. And if we make some trajectory for querying the model, we can get smooth video render. So no more mess anymore, you can relax. And let's finally look at the render results and see how powerful NeRF is. That is it. Here is our tractor from training examples. As I remember, all these things were rendered something about 80 images. And as you see, it's able to represent such complex structure as this tree with all these leaves and twigs. But for now, let's pay attention to the water around the ship. You can see all the reflections of light in the water, which were captured during the change in camera position with respect to the light source. And on the right, there is a detailed pixel values, what changed with different viewing directions. For me, it looks really incredible. We reconstructed a 3D scenes with all the reflections and lightnings from the raw pictures taken around an object. But I need to warn you, this is not a magic. NeRF can't guess a scene that he has barely seen. Neural network just learns to interpolate between known images, and if you pass like arbitrary set of images, and if you want to reconstruct the scene from arbitrary set of images, it could be not possible because sometimes it not covers scene properly. Now, let's talk a bit about some NeRF improvements. Believe me, it will impress you. After the original NeRF paper had been invented, it became a hot topic. A lot of research had been done by scientists, and one of them is NeRF. As you see, the idea is instead of training one big neural network for the whole scene, to create multiple ones for each small part and call it depending on the position. It's highly increased the prediction time, but what is more important, further amazing work named block NeRF was done based on this idea. They used images from self-driving vehicles captured from the part of the real city. The city was divided by blocks with its own NeRF submodel, and the same it was with KiloNeRF. Another awesome work done by the NVIDIA research team named Instant NGP. We won't review their architecture contribution because it's pretty complicated. Let's just look at the results they got. You can see their NVIDIA render of some room. Like here is the man standing near some table. And for me, it looks really incredible. It looks like we stopped the time in the room and just flying within it. And on the right, there is render of my own boots from images done just in the hall. Shame on me, they are a bit dirty. And the most exciting part is that all this were trained in less than 30 seconds. This is really far-reaching progress because, as you remember, initial models have been trained something about a day, but here, like, it's just in seconds. After viewing these entertaining videos, let's talk a bit about some drawbacks. I'm going to compare NeRF with similar approach for scene reconstruction called photogrammetry. Just a few words about it. Photogrammetry's goal is scene reconstruction from the point of cloud and conversion to a mesh. It is done by mathematically matching the key points among all of the images. First point to compare is accuracy. In general, NeRF is a bit more accurate than the photogrammetry, but if you want to scan some real, small and detailized object as accurate as it could be, you probably need another tool named 3D scanner. But if you can afford some small inaccuracies, NeRF and photogrammetry are doing pretty well. Next point, what NeRF achieved is capturing the light. If you try to use photogrammetry with any reflective or transparent object, it completely distorts reconstruction results. So basically, you can't use it with a lot of objects in the real world. There are ways to handle this problem, like fully covering with some powder the object to get rid of all the reflections and light interactions, but we'll lose the texture of an object. And basically, not only reflections causes the problem. If you remember the tree scene from the previous render examples with this scene twigs and leaves, that also be a problem for photogrammetry. So here, NeRF definitely has a point. But next is a NeRF weak point. As you probably guessed, all the computation around NeRF is going on GPU accelerators. When I tried to reproduce and render some results, I often faced the lack of GPU memory. For the latest NeRF technology, you need at least 12 GB in your GPU to train a network with decent results. Similar situation is with photogrammetry. So considering today GPU prices, this point is quite unpleasant. The next point is hunger for the data. If you don't cover scene properly, NeRF can't properly interpolate between images and would output just some noise. But NeRF feature that it learns to interpolate between images, but alternative doesn't. I found some comparison between NeRF and photogrammetry in senior construction with low amount of images. It showed that when NeRF generated just a bit inaccurate results, photogrammetry offered nothing, because photos captured for photogrammetry should overlap consistently to match the key points. Next is one of the most important points for NeRF. It's probably the key drawback to make it an obvious winner. We can't accurately extract mesh from it. The main goal of NeRF is optimizing to scene implicitly in some inner structure, like weights of neural network or something else. And using the common algorithms to convert it to some explicit form sometimes can cause inaccuracies with small and detailized object. But on another side, photogrammetry main target is mesh extraction, and it's the way it represents the scene. And finally, the most important point for NeRF is that it's really young. It was invented just 2 years ago and continues to improve. Every 3 or 4 months, researchers publish new papers with new ideas and developments. I heard about some ongoing research about mesh extraction, like some more explicit ways to represent the scene. And as you remember, time for training the first NeRF models was something about days, but now it's just the seconds, like with even more accuracy. So it's just a matter of time when everything would be solved and we all would start to use this. This is all the comparisons. I believed I pictured all the important sites. Now, let's talk about some possible uses of this technology. Really exciting application is using neural renderings for virtual reality scenes. Imagine you can wear a virtual helmet, appear in some real shopping center that was rendered without manually creating in some 3D graphical software, with all the reflections and lighting effects remains as it was in the original. All the shops are open, all the goods lies on shelves, and you can see the prices, put some clothes on the shelf with some other deep learning technologies. Or another example, visit your friend's apartment and walk through it. What he was just sending to you in the messenger, because everyone can reconstruct any scene and embed it to virtual reality, just capturing the scene around themselves using his smartphone. Next is use neural rendering for product scanning. After vendors scan some object and upload it to the product page, you can view it from every side, or even try to place it somewhere around you using adjusted reality with your phone. Look from all the sides and see whether it suits here or not. I believe it is pretty cool. Another useful application is universal explicit reconstruction to assist 3D graphical designers in creating 3D models. NeRF's ability to represent scene as it was is just amazing. But as I said before, it is done in some specific way. There is some algorithms to convert to explicit form, but often it struggles. But when it is solved, neural rendering will definitely be the king in 3D reconstructions. About other applications, you can think on your own and share it if you want. That's it. Hope you enjoy my report, and if you have some questions, I'm glad to answer.
We will check everything on our side. Yeah. So, do you hear us? See us?
Yeah.
Great, great. Thank you very much for your lecture, and if you're ready for any questions, let's start. So first of all, we'll do a question from my side, if you don't mind. So what is your, let's say, best recommendations in terms of maybe books or some lectures about your topic, if someone would like to jump in the data science and data topic? So like the beginner level, let's say.
At first, I need to say that neural rendering is not only about the neural networks. The recent technologies is really broad. There are a lot of computer science used in it, so probably you need to know something about computer science and some basic knowledge of neural networks from the machine learning.
Yeah, and how had you get to this point? So did you remember that when you was a child, you were like dreaming about science and data science, or it just like evolutionarily came from a development perspective? So what was your career path?
It's partly of both. When I was a child, as I remember, always thinking about the developers and the engineer work, and it just evolved to being a data scientist and machine learning engineer.
Yep.
So something like this.
Yeah, that's really great. And the last question from the studio before we jump into another one. Could you please tell us how do you recommend to our new speakers and viewers how to better prepare yourself to the presentation? So you did a really great job. Like you conducted presentations despite of the fact of some tech difficulties with the sound and all the stuff. So you was calm, you were calm and did a great job. So what is your best tips and tricks that you can share?
I believe there is no like some hidden secrets what I have. The only way to do your work good is just to do it. You need to like cover the topic as much as you can, to explain it as much as you can for everybody to get your point, and just do your best. So nothing hidden.
Yeah, totally agree with you.
Okay, and I have one more question for you. What was the most challenging situation in your career, in your job?
To tell the truth, probably I never reached some real hard situation. Probably is what first came in my mind is to apply for the job. It's really hard for every newbie. So except this, I believe all my problems and the hard points is on my way.
Yeah, that's great. That's really awesome. And thank you very much for your time and for your lecture. It was really good to see you.
Thank you.
Thank you.
Yeah, see ya.
Do we have like time for answering other questions?
Yeah. So.
Okay. First question I see, does NeRF have any technique to deal with noise in input images? So my question is yes and not really yes. There is some techniques for like in general, if you try really, if you pass really a lot of images to the NeRF model, and some of them would be a bit noisy, probably NeRF can handle this because like every other images is clear and model can clearly learn something from these images. But it would be just some not really bad for the model if one of the photos would be some noisy. The next question is, what do you think is the future of neural rendering? I believe the future of neural rendering can perform best in the virtual reality, as I already said. Tendency to transfer in real world from to the virtual one is really explicit. So NeRF ability to help us with this is just amazing. So I believe it would help us in the future. For what cases do you think photogrammetry would be enough? As I already mentioned in my comparison, photogrammetry produces pretty similar results in accuracy, but it often struggles when we try to use it for some really complicated scenes and where we have some lighting conditions. For example, if you want to capture a scene with just the cup, as you see, there is no light interaction or something like this. Photogrammetry, like just simple, straightforward tool to do this. But like if you want to capture some huge scene, like for example this shopping center, it would be impossible using photogrammetry. For what case? Next question. So NeRF is built a separate model for each single scene. Is there a way we use one model for multiple scenes, or at least pre-train it to some domain to decrease amount of time for training? Yeah, there is some works about this. As if you know something about the convolution operation, the idea in that work that we can use some pre-trained models on the ImageNet dataset, if you know this, to get some embeddings from the images and deal with these embeddings. And I believe it can reduce the training time instead, like in representing some hidden states of the images. So yeah, there is such work about this. How many images is enough to build a high quality scene? Does this number decrease with NeRF model size growth? Answering the last part of the question, I believe no. Increasing the models power didn't decrease NeRF's scene representation accuracy. The explanation is like if we have some object, saying like my hand, and two positions of camera and two shots, and there is no way to predict scene accurately if we have just two images, and if we query somewhere here, no way for the model to reconstruct the scene properly. And the first part of the question, how many images is enough to build high quality scenes? It depends what do you mean by high quality. If you like reconstructed that room from the render examples of instant NGP and try to zoom to some certain point, there would be some noise because there were no images of that particular texture in such close in such close way. So to represent scene details as more accurate, you just need to capture these scene details as more than accurate. So something like this. If you just to summarize, if you want to capture the scene from only one point, like standing inside the room and looking at every corner, that would be enough just to capture the room around you. But if you want to fly within every part of the room, you need to take more shots. Is it possible to add a new object to the scene that produces NeRF with no need to retrain the whole neural network? Yeah, it is possible. The first way to do this, as I said, to extract mesh from the scene and like manually add something using some 3D graphical software. Like it's a more straightforward way. But another one is represent scene more explicitly, that you can edit something in your representation of a scene to be able to edit it. For example, the latest work what I have shown, Instant NGP represents things not only with neural networks but also with a voxel grid. So you can edit something in this voxel grid more explicitly to be confident that it wouldn't be just some random changing of the network behavior. So yeah, and actually there is more simply ways to do this. I saw some works about people reconstruction, like there were some men and women standing, and they captured their position. And another ability what they allow you to do is like to change the type of body. You can like add some muscles, add some fat to the man, and something like this. So it is another way to do this. So that's pretty all the questions. Thank you. Thank you.
Yeah, thank you, Timur. You too. So you get a really great job, both selections and all those questions. So it was really interesting to step into a data topic and get a new knowledge from you. Thank you very much.
Thank you.
Thank you. Bye.
Bye.